Hey guys, it's Miss Van Tassel. So this lesson we're going to be talking about a normal distribution. And so a normal distribution is what we call a bell-shaped curve. And so I kind of drew our bell-shaped curve here, some properties of our normal distribution curve or our bell-shaped curve, or they also call it just a normal curve, are that it's symmetrical, about the mean, and the mean is directly in the middle. So here's our mean, and it should be symmetrical about that line. It has tails on both ends, and those tails should also be symmetrical. And it has a mound in the middle, meaning that the majority of your data is going to fall in the middle of the normal curve. It's actually one way to represent data is with a histogram, and it's actually really easy to see from a histogram if you have a normal curve or not. One way to do it is just to kind of draw a curve like around your histogram. So if I kind of drew a curve going over my histogram here, you'll see that same like bell-shaped curve, and so it looks like the data in this histogram example is normally distributed. Okay, and so standard deviation. Standard deviation is looking at the spread of your data. We denote it with the symbol sigma, and so what sigma looks like is it's like a circle with a little tail at the end, and so that's a Greek letter sigma, and in statistics we use sigma strictly for standard deviation, more specifically of the whole population, but I'm not really going to get into that at this point. So just know sigma is your standard deviation. So what does standard deviation matter? If you look down below, there's 3 different normal bell-shaped curves. We have the blue one, we have the red one, and we have the green. I think that's green. I don't know, green, yellow. And so you'll notice that the middle, so that the average or the mean is the same for all of these. But each of these has a different standard deviation, or how far the data is spread. So when the standard deviation is 2, you notice that the mound is much bigger in the middle, but doesn't kind of go out as far as the rest. And then when the standard deviation is 3, the mound is a little bit shorter in the middle, and then here we have a much flatter mound when the standard deviation is 5. So it's just is like taking that that curve and it's like spreading it out more, if that makes sense. So the higher the standard deviation, the more pulled out your normal curve is. Yeah, and so I want to take a look at how to draw a normal curve, just given some information. So for this example, it says adult female heights are normally distributed with a mean of 64 inches and a standard deviation of 3 inches. So I'm just going to draw right in the middle my mean. So my mean is 64. And then typically with normal distributions, we really don't go much further than 3 standard deviations out on both sides. So I'm going to add 3 for my next marks. This is 67. Then I'm going to go 3 more, 70, 73. And so this is 1 standard deviation, 2 standard deviations, 3 standard deviations, and then this is the mean. And then I'm also going to go the other way. So 61, 58, 55. And so -1 standard deviation from the mean, -2 standard deviations from the mean, and -3 standard deviations from the mean. Okay. And so from here, I know that my mound is going to be directly in the middle, so it's going to look something like that. All right, so here's our mean. It goes in the middle. With normal curves, 50% of your data is to the left of the mean, and 50% of your data is to the right of the mean. And so there is a way with normal curves to determine how much of your data falls within a certain amount. And so we're going to start with how to use the Z formula to figure this out. And so this is going to be a little bit weird at first, but you'll get used to it. And so I want to start with just what some of these symbols are. So the Z formula is x minus mu over sigma. And so we'll start with x. X is just your, like, the data value that you're looking for. So if I want to know, like, what's the probability of something being less than 35, then my data value would be 35. Mu is this little, like, U symbol. This is the mean, and more specifically, it's the population mean. Okay. And then sigma we already talked about is the standard deviation. And also, more specifically, it should be the population standard deviation. Okay. Once you get your Z number, because you're going to fill these in. So once you get your, whatever your Z number is, you're going to go to your Z table. And so the nice thing is that if you just search Z table in your, like, search bar, you're going to get a million of them in the images. So you can just click on one if you need to. But the way a Z table works, so you'll get your Z score from your Z formula. Then what you're going to do is you're going to look at your chart. And so I have an example of a chart here. So the rows and columns are your Z score. So you'll notice that you're going to start with the rows first. And you'll find, like, let's say your number is we'll use 1.67 since it's already highlighted. So I will go down to 1.6, and then the columns are my hundredths place. So 1.67 would be 1.6 in the rows, and then all the way to 7 in the columns. And so right here is where they meet. And so inside the chart is your probability. But it's specifically, so this is important, it's the probability that the data value is less than or equal to x. So less than or equal is important. So if I wanted to know what the probability of it being more than that was, I would have to do 1 minus my probability, which is 0.95254, and then figure that out. So less than, you can always look right at your value, and that's just your answer. But if it's greater than, then you're going to have to take the probability and subtract it from 1. Okay, so that's really, really important. All right, let's continue on. So let's look at an example where we would be using the Z formula. So it says Hippie Chip cookies are sold in 32-ounce packages. The company claims that the mean weight of the package is 32. So I'm going to just stop right there and just kind of make little notes for myself. So my mean weight is 32 with a standard deviation of 0.6 ounces. So my sigma is 0.6 ounces. What is the probability that a package contains more than, so that already tells me I'm going to have to subtract from 1 if I'm using my z-chart, 33 ounces. So my x, I'm looking for the probability that x is bigger than 33. And so my x that I'm going to use is 33 in my z-score formula. So first thing I need to do is find my z-score. So my z-score is equal to x, so 33, minus my mean, 32, over 0.6. And so I'm going to plug that right into my calculator. And I get approximately 1.7. So once I get that score is gonna tell me where in my table to look. So I'm gonna go back to the table and find I guess it was 1.67 if we're going to the hundredths place. Okay. So I already showed you guys how to find that one specifically. So we would look here, 1.6, then go out until we get to 1.67. And so remember that this probability, the 0.95254, is the probability that x is less than or equal to 33. I forgot what the number was already. 95254. So the probability that x is less than or equal to 33 is 0.95254. But I want the probability that it's more than 33, and so I would just take this value and subtract it from 1. So the probability that x is greater than 33 is going to equal 1 minus 0.95254, which is 0.04746, which means that it's approximately 4.7%. So 4.7%. There's a 4.7% chance that my package is going to contain more than 33 ounces. You can leave it just as a decimal, though. You don't have to turn it into a percent. All right. So the empirical rule. So what the empirical rule says, and so it's got a nice sounding catch to it, but it's 68, 95, 99.7. And so what those numbers mean is they mean that 68% of the data is going to fall within 1 standard deviation from the mean. So that goes from 1 less than the mean to 1 more than the mean. So that's this yellow area here. Okay, so that's 68% of the data falls within that area. And then 95 is the amount of values, or the probability, that your values are going to fall within 2 standard deviations of the mean. So from here to here represents 95% of the data. And then the final, so 99.7 is going to represent 3 standard deviations from the mean. So 99.7% of the data is going to fall within -3 standard deviations to +3 standard deviations from the mean. So that's what the empirical rule is stating. And our last example. So the number of candies in a bag is normally distributed with a mean of 32. So I'm just going to make a note that my mean is 32 and a standard deviation of 2. Approximately what percent of the bags contain between 30 and 34 candies? So if I was making a normal curve, my mean goes in the middle, and my standard deviation is 2, so then it would go 34, 36, 38, 30, 28, 26, and I want to know how much is going to fall between here and here, and so that's within 1 standard deviation from the mean, and so 1 standard deviation from the mean represents 65% of the data. So approximately 65% of the data, or 65% of the bags would contain between 30 and 34 candies. Well, I hope that this helped clear some things up for you if you're having trouble. I know it was like a quick rundown of normal distribution. So if you have any extra questions, please reach out to one of us to help you. And I hope that you guys are staying safe. Talk to you soon.